This is now the first session on hardware security. You are in the plenary theater. If you don't want to hear anything about hardware security, now is your time to leave. Please don't do that once the session starts and people are talking. We'll have 3 talks in this session. Talks are 25 minutes. And the first talk is actually going to be given by 2 people, by Fabian and by Georg. And they are going to introduce to us HADES, Automated Hardware Design Exploration for Cryptographic Primitives. And the floor is yours, and I'm actually going to hop down here because I want to see your slides.
Okay. Thank you very much for the introduction, and welcome to our talk. This is a joint work together with Niklas Höher, Jan Richter-Brockmann, Pascal Sastrich, and Tim Günesu, all from the Ruhr University in Bochum, Germany, or in the case of Georg, formerly RUB and now Intel. So I want to start with a small motivation, why we did this work, and give you some technical details about our concept before Georg will take over with the case studies. So for the motivation, I first want to talk about 2 aspects of this very long title. On the one hand, efficient cryptographic hardware, and on the other hand, secure cryptographic hardware. Starting with efficient cryptography. So usually when we talk about efficiency, we mean efficiency relative to a certain performance metric. So for example, the latency in clock cycles, the area in gate equivalent, or the delay. And when we implement a cryptographic algorithm in hardware, we usually have to make many different design choices that influence the performance metrics of our design. And to influence this, I want to give you a very small example. So let's assume that we have a 4-bit function S, such as an S box, and we want to apply this function to an 8-bit state, so to the lower 4 bits and to the upper 4 bits. Then if we want to implement this in hardware, we can think of 2 ways to implement this. The first one would be a parallel architecture, where we have 2 S boxes in parallel, and the advantage of this implementation is, of course, that it's faster, but on the downside it also consumes more area. And then the second way we could implement this would be a serialized architecture, where we only have 1 S box, and first we apply the S box to the lower 4 bits, and then once this is done, we also apply it to the upper 4 bits. And you can see that this consumes less area because we only have 1 S box, but it's also a slower implementation. And usually we have to make many different design decisions similar to this, sometimes way more complicated. And because this adds so much complexity to our design process, it gets really difficult for a developer to always make the right design choice to reach the most ideal design with regards to, for example, the latency. And the second part I want to talk about is the secure cryptography. So one might think that a secure cryptographic algorithm that we are running on a chip or something like this is always secure. But of course, here at CHES, we know that this is not true because of physical attacks. And what I want to talk mostly about is side-channel attacks, where an attacker monitors the physical characteristics of a chip during execution, and for example, through the power consumption, can learn secrets like the secret key that you usually shouldn't be able to learn. And one of the most popular countermeasures is masking, where we split up the secret into multiple randomized shares, and then we only do the operations on these shares and not the secret anymore. And this is quite easy for linear functions, which we simply have to replicate. But for nonlinear functions, this gets really complicated because we have to sometimes add register stages, add fresh randomness, and overall it just gets way more complex. And so if you want to mask an entire circuit, that's very, very complex. And what we often do is we apply so-called gadget-based masking, where we only design certain rather small, very important functions, so-called gadgets, and design them in a secure way. And then we can construct an entire circuit based on these gadgets by simply replacing insecure parts of our circuit with their secure counterparts. And there are multiple different gadgets that have different performance characteristics with regards to latency, randomness demand, and area. And so in addition to all the design choices that designers have to make for their hardware implementation, if we also want to consider physical security, we get additional design choices that we have to consider. And so the question that we asked ourselves was, is it possible to create an automated and efficient and security-aware design flow for cryptographic primitives? And of course, since we're standing here, that is possible, and our concept is what is HADES. And HARDES is based on what we call templates, and templates have some similarities to entities or modules in Verilog and VHDL. So they are basic building blocks to construct larger hardware circuits. They share some similarities, but they also have additional information and metadata to allow a security-aware and efficient design space exploration. And I want to briefly talk you through the different parts of the templates. So what we first have is what we call algorithm parameters. And these algorithm parameters change the functionality of the template. So this could, for example, be the width of an adder or the key size of the AES. And what we also have is the interface of the template, which is basically just the input and the output signals or the control signals. So far, that's quite similar to entities and modules. Now comes the interesting stuff. What templates now also have is what we call design aspects. And these design aspects do not change the external functionality of the template, but they change how internally the desired functionality of the template is achieved. For example, this could be the type of the adder. So do we want to use a Sklansky adder or a ripple carry adder? The parallelism, so how many different S boxes do we want to use? And so we have, for each template, many different design aspects, and each aspect can have multiple different options. Then what the template also has is the hardware security context, and this basically defines the security goals that we want to achieve. So do we want to achieve side channel security? Do we want to achieve fault security? And in our case, the hardware security context is usually the masking degree. And then quite similar to the design aspects, we also have the hardware security aspects, which are basically how do we achieve the desired hardware security. And in the context of masking, this could be the gadget type. So for example, the HPC2 gadget or the HPC3 gadget. And then quite similar to entities and modules, we also have a hardware description, which basically tells us how do we calculate the outputs based on the inputs. And of course, this hardware description has to take into account the algorithm parameters, the design aspects, and maybe also the hardware security aspect. And of course, each template can use an arbitrary number of sub-templates, just like each module can have various sub-modules. And now that I've talked you through the template, I want to briefly go over the design flow of HARDES. So in HARDES, we distinguish between template developers and template users. So on the one hand, we have the template developers who are experts in hardware development. And what they do is they design hopefully well-written templates in some kind of template library that then the template users who might not be so familiar with hardware can use. And template users can use HARDES via a simple JSON file where they can give in some algorithm parameters, the desired hardware security context, the desired optimization goals, and some more things. And then the design space exploration in HARDES actually starts. And it starts with the configuration extraction. So HARDES goes over all the templates in the template hierarchy and extracts all possible combinations of configurations. So for example, if we have a hierarchy like this with only 2 templates, and let's just assume that the top level template has 2 different design aspects, and the sub-template also has 2 design aspects, and in total we have 2 hardware security aspects, then we simply extract all possible combinations of these things. So this would be a list of 8 possible configurations. And then we do the actual design space exploration procedure, where we really go through all the configurations in our list and extract the performance. And this happens in a bottom-up procedure. So if our hierarchy looks like this, then first the lowest sub-template would report its performance metrics up to the next highest sub-template. Then those would report their performance metrics to the top-level template. And then in the end, the top-level template gives us the overall performance prediction. And based off these performance predictions for every configuration, we get, on the one hand, a list with all the best performing configurations. And we can also, of course, generate the best performing designs either in Verilog or VHDL. And with this being said, I will hand over to Georg for the case studies.
Thanks. As Fabian already indicated, we did not just formulate the concept and also implement a proof of concept tool, but we also carried out a wide range of case studies, really starting with small functionalities like addition or modular addition, But with addition, we can already achieve ARX ciphers to be masked, and actually we could not find another masked implementation of CHES or masked hardware implementation of CHES. So this should be the first one, and in the design space exploration, in the end, actually we arrived at a more than 1 terabyte throughput. Of course, it's huge, but yeah. So in the remainder of the talk, however, I want to focus on these two case studies, namely AES, because it's such an important benchmark for masked hardware, of course, and MLChem, well, because it's been a hot topic lately. So for AES, this is more or less our design space. So our template supports choosing the architecture, choosing how many S boxes we instantiate in the key schedule or in the round function with an option to just reuse the S boxes from the key schedule. Also, the type of the S box can be chosen, and of course also the type of the gadget. And this yields 4032. So it's a bit of a simplification here, but overall this yielded 4032 different designs that were explored by our proof of concept tool in about 10 seconds. So explored and the performance predicted. And now to compare this to other works, here are 3 graphs that represent the basic hardware trade-offs for masked cryptographic hardware. So area versus latency, area versus randomness, latency versus randomness. So in all of the 3 graphs, it's better to be closer to the bottom left corner. And what you can see here are the handcrafted implementations from the last decade and a little bit more. And yeah, that's about that. And the first thing that we would need to compare to is AGEMA, of course. AGEMA is a very nice tool presented at CHES 3 years ago. And AGEMA is a netlist transformer. That means AGEMA takes an already synthesized netlist and uses the same principle of gadget-based masking to replace the insecure data path with a secure data path, more or less. But since it's working post-synthesis, of course, it's not capable of doing a design space exploration apart from the gadgets that are used. So that's certainly a limitation. And now here you can see the results of Hades. And what sticks out is that both AGEMA and Hades are actually capable of producing designs that come very, very close in performance to the handcrafted designs. Of course, they are not yet, let's say, outperforming handcrafted designs, but I think that shows really nicely how far design automation in masked circuits has come. The second case study I want to talk about is MLChem or Kyber. And so you might have asked yourselves how this should be possible with gadget-based masking, so with Boolean masking only. And the idea that we follow here is a paper that has been presented at CHES last year, where the polynomial multiplication in certain cases can be actually carried out in Boolean masking. The condition is that one operand is public and the other one is secret and only has small operands, so small coefficients, and this is the case in MLChem. And that what we can do is actually so on the coefficient level, first we can compute all the potential multiplication outcomes, and then in the masked part we just have a multiplexer to select the correct result, and then we obviously need to accumulate all these results with a masked adder. So it's basically a polynomial multiplication by a secure addition. Of course, this leads to a little bit of a nonsensical situation, because for a valid MLChem, then we need to perform an inverse entity on the matrix A, such that we can actually apply the schoolbook methods. But for now, that's about the possible way to implement this with gadget-based masking. The design space then is a lot of options for the parallelism. So how many parallel adder stages do we have in the polynomial multiplication multiplier? So how many compress1 gadgets do we have? The number of the key steps in Ketchak, how many do we have in parallel, and of course, again, also the gadget. And this resulted in more than 1 million different designs. And here you can see the performance prediction for the exhaustive search took about 36 hours on a standard laptop, I believe. And in the paper, just have to point you to the paper here, we also discuss ways to make this faster at cost of a little bit of accuracy in the prediction. And then this can be stripped down to a couple of minutes. So let's have a look on the results. For the unmasked circuit, what you can see is there's always this basic trade-off that we have in hardware. So it's either we have a very low latency but very huge design. In fact, it's so huge that we couldn't even synthesize it. That's why there's a dash at the synthesized area. So it's the synthesis took more than 72 hours. That was kind of our cutoff for the paper. And on the other hand, we have the area-optimized implementation that takes 20 million cycles. That's because the arithmetic runs on a single full adder. The same trade-off is also there for the masked, first-order masking. And you can see now the latency-optimized version, the area goes into the megagate equivalence. On the other hand, the area-optimized implementation, of course, didn't get any faster. But what you also can see is that the tool found a very nice trade-off. So the area latency product minimization had really so at the cost basically of double the latency from the latency optimized version, we could strip down most of the randomness, most of the area, and so I think that's a very nice result. So if you go back to this area optimized implementation, you might ask yourselves two questions. The first is, why is it still so huge? And the second is, why is there such a discrepancy between the estimation and the actual synthesis? So why is it still so huge? It's a very important point about our concept. If we have a template that is written, let's say, in a non-optimal way, let's say by a late-stage PhD student who didn't have too much time to put into this, then the tool cannot correct this. So the tool only explores the design space that is given by the template. In this case, for example, we have one Ketchuk for the expansion of A and one masked Ketchuk for sample CBD and all this stuff. So there's always a huge space goes into the Ketchuk states. And the second thing is this thing that we always still need an inverse NTT module, of course. Then where does this discrepancy between the estimation and the actual synthesis come from? And this is because in our proof of concept tool, we only estimate the size of the secret data path, which is usually the limiting factor, or the largest factor in masked implementations. In principle, nothing speaks against also estimating the size of the public data path or estimating the size of state machines. It's just more effort, and usually, so the order of the outcomes doesn't change, actually. So that brings me to the end. I want to mention some things that I really would like to see in the future. First, of course, we would like to see arithmetic masking being supported. There's a bit of background theory work to be done here, because so a lot of these composability notions in hardware and transitional stuff needs to be resolved there, but I think that could come kind of soon. Then, of course, what you also have seen is there's a lot of room for optimization, and in the past years, what we've seen is there are several works that go into the optimization, for example, of randomness, to reduce randomness, to reuse randomness, even in gadget-based masking, or mixing gadgets. So currently we have to decide on one gadget, but we also know of the benefits of mixing the gadget types. And finally, I would also like to see formal verification being integrated. So formal verification of implementation security properties, or formal verification of the correctness, and things like this. That's it. Thanks. And are there any questions?
Thank you. Thank you for staying on time. Questions? We have microphones here and here, don't be shy. Okay. While people collect, he's running. Okay. Question coming, Patrick?
Yeah, thank you for the presentation, very nice work. I was wondering, do you have a concept of optimality in your search?
There is, I mean, we do an exhaustive search, and then based on the exhaustive search, we can say this is the optimal result given that template. So given any potential design space, it's obviously not optimal, because there could be always something better.
But the template captures the whole design space, right? So at some point you need to bring in constraints and say, I want to have the smallest design at this speed.
Yes, but I mean the tool is capable of just selecting the smallest design.
Okay, so that's part of the template.
That's part of the tool, I'd say, not part of the template.
Thank you.
More questions? Okay, I have one question. Can you explain what exactly does it mean when you explore the design space? Like, do you you synthesize for every possible option? Because this seemed to be extremely fast.
Yeah,
or like, is it pre-synthesized and you just put things together?
No, that's exactly the point. We don't want to synthesize every possible design because that would take ages. So what we actually do is we kind of count the amount of gadgets that we have. We count the amount of AND gadgets that we have, the amount of XOR gates or gadgets, the amount of registers, and we have pre-synthesized a list with the approximate size of these gadgets, and then it's basically just if we have 100 AND gadgets at the cost of, I don't know, 200 gate equivalents, then it's 100 times 200, the area of the AND.
Okay, that makes a lot more sense. Thanks a lot. More questions? No? Then let's thank the speakers again. And I ask the second speaker to the stage. Here comes Francesco.
Hello, everybody.
Okay, second speaker is Francesco, and Francesco is going to speak about a framework for secure third-party IP integration into NOC-based systems on chip platforms. Floor is yours.
All right, thank you for the introduction, and welcome everyone to this presentation. I'm Francesco Restuccia. I'm a postdoc at the University of California, San Diego. I work with Professor Ryan Kastner. And today I'm presenting this work that I've done in collaboration with my colleagues at UCSD, Zhonghua Ma, Andres Meza, and Ryan Kastner, of course, in collaboration with Columbia University team, Luca Carloni's team, in particular Joseph Zuckerman, Brooks Ayum, and Luca Carloni. So just to start with an introduction on the rise of open source system-on-chip platforms. This does not intend to be like an exhaustive representation of what is available, but just what I've been happen to work with or to know better. So there are a lot of open source system on chip that became very mature and very interesting for me because they allow to democratize the access to custom system on chip platforms. In particular, we're going to focus a little bit on ESP because its part has been used in this project. So ESP is a project that provides a tile-based infrastructure to make custom system on chips. And basically starting from open source projects or also closed source API, it provides a platform for integrating them from using an hardware flow that allows to integrate third-party IPs inside of a system on chip that integrates a CPU and a memory tile, and it provides also a software flow that is capable of running Linux or providing some bare metal support for making the hardware executing. And what we have coming out of the flow is something similar to this. This is just a sample architecture, 3x3, ESP system on chip. We have here 2 accelerators, 1 CPU tile, 1 memory tile, 1 I/O tile, and I'm going to go a little bit deeper in detail after that. So I just say that these SoC platforms are pretty mature. So what is the motivation of this work? Well, they're very mature in functionality. There have been multiple tape-outs for these platforms, but unfortunately, despite the car attractions, there are very limited. There is very limited focus on robust security features on these platforms. So basically, our contribution here is Bastion, which is a framework for the integration of third-party IPs, the secure integration of third-party IPs in network-on-chip-based platforms. And our contribution can be summarized in 4 sub-contributions, which is a distributed access control system and a distributed security infrastructure, for network-on-chip-based SSD platforms. And we're going to focus on access control. I'm going to show you why in particular. An extensible security verification framework, the analysis, an analysis of how to configure the access control system on the network on chip securely, and the open source integration so that you can use it right away with the ESP platform. This is the repo. We have an open source repo. If you want to check out the code, I'm going to share after a QR code, so it's going to be easier to access. So I mentioned before, why should we focus on access control? Well, Mitre, every 4 years, at least the latest from Mitre was 2021, and recently there was this 2025 release 2 weeks ago, I think, of the most important hardware vulnerabilities found, weaknesses, found in industrial design. And there are very important issues here, but if we look more in detail, 5 out of the 11 individuated by Mitre are related to access control. So this is something that it is stable in time. It was similar in the previous table provided by Mitre. So we've been working on access controls in the past because we saw this interest. And after this introduction, I can introduce a very brief and high-level threat model that we considered. So in our case, we follow a typical ESP development flow. We want to integrate third-party IPs that can go through different flows. We assume the network on chip to be trusted from ESP, and we assume that we have a trusted entity for configuration inside of the system. What we are interested in is that the third-party IPs might not be trusted, so they can have malicious hardware parts, or they might even be taken over from software vulnerabilities and attempt to access memories that it should not supposed to. And our goal is to provide a lightweight system to enforce access control on the network on chip, and detect illegal attempts and eventually take correction on that. All right, so let's dip a little bit into the architecture of Bastion. So first of all, just the architecture of ESP. This is a 3x3 network on chip design. We have 9 tiles, each which include 1 or multiple IPs. We have 2 different accelerators that we consider third-party IP in this representation, and 1 CPU tile, and 1 shared memory tile, and an IO tile. So just to look a little bit what can be an accelerator, this is just a high-level representation. This is a sample accelerator that comes, for instance, from the ESP flow for HLS design accelerators. Or this is an NVDLA core that has been integrated using the third-party IP flow from ESP. And then we have an IO privilege tile. That is the tile that it is privileged with respect to the others because it's the one that is in charge of making the configuration of the system, and is also one that we're going to use for the configuration of our access control system. Overall, this is the architecture, so you might have seen that in all of them, while I was going through all of them, there was this red box that is like actually our security socket, what we call a socket or security socket. And basically, this is integrated each in a tile, and it provides a distributed access control system for the network on chip that can communicate with the trusted entity that we have in the IO tile. Let's get a little bit into the socket internals. This is a pretty straightforward logic. The logic itself has been placed between the queues, and there are some reasons for that I'm going to show you later. why I decided to do that. And it has, these are the two interfaces between the core and the network on chip. And as I mentioned before, we need a secure configuration, and the secure configuration comes from the network on chip, and in particular from a secure data plane that allows to configure the access control list, the local access control list inside of each tile. So why should we integrate the access control socket inside between the two queues and between the tile and the network on chip? Well, in this way, we have a native integration with the network on chip such that we don't have to make any conversion of protocol, basically. So anything that is supported by ESP or the network on chip in which you want to deploy your access control system is supported by our system. There is a lower impact on performance because we don't need any bridges to convert protocols between access control and the accelerators in case we put it before the queues. But also the illegal transaction itself are stopped at the source, so the difference is that if we have put access control at the resources, we would have to propagate back errors to say that the transaction was illegal, in particular with specific protocols that require, on-chip communication protocols that require error to complete the transaction, otherwise stalling the transactions. Okay, moving now to the security verification flow that we have for Bastion. So the first part was design, and right now we have the security verification. So we aim to provide a security verification flow. And this is the 6-step verification flow that we use for Bastion. We use the CHES tool for information flow traffic verification. And we got a security verification that is on 3 different levels, AP level, firmware level, and system level. I'm going to go through just one single example that is on the communication level. And we have the 6 steps. The first step is to define the threat model. In reality, it's more like refining the threat model. We have the threat model from the beginning that I showed you before, and we just refine it for the specific level that we are considering. And in this case, what we refine is we define that the configuration coming from the trusted entity over the security network on chip plane is trusted. Following, we identify the assets. In this case, the assets for us are the registers that are internal to the security sockets and then contain the access, the local access control policy. And then we identify the potential weaknesses. To do that, we look into the CWS, and we did a manual process to selecting the CWS for this project. There are methodology for automating that, of course, but in our case, we wanted to be sure to evaluate all of the CWS, so we did a manual process to analyze them. Following, we define security requirements for the property, and in this case, the security requirements is that the configuration register contain the default values until it is modified, actually, by the trusted entity. And from that, we specify the security property. In this case, the property is specified using the Radix language, using the no-flow operator. This is a convenient way to define properties for access control. And after that, we use the security tool for verifying the properties. This is just one of the properties. In the paper, there are more properties if you are interested, and we are gonna make available also the properties in the repo soon. Finally, the experimental evaluation for performance and area impact. We conducted a 2-fold experimental validation. The first one is just an implementation of the S-socket on FPGA to evaluate the S-socket with respect to the standard socket of ESP. We just provide routing functionalities. And then we did a case study in which we implemented a full system, 2 full systems actually, a 2x2 and a 3x3 system. The architecture is presented over there for the 2x2. For the 3x3 is pretty similar. There is a memory tile, an accelerator tile, which in this case is a GEM accelerator tile, an I/O tile, and a CVSX processor tile. And we deployed this on FPGA Virtex 7 Ultrascale Plus, and we collected the data actually from the FPGA. So the first one is the performance impact that we see for our system. We have two different, as I mentioned, two different experiments, 2x2 versus 3x3, and in two different shades of light blue and two different shades of orange. We have the standard ESP system and the ESP system plus Bastion. The first set of experiments on the x-axis, you have the transfer size that we make between the accelerator tile and the memory tile. And on the y-axis, you have the clock cycle, the latency to complete data transfer. So what we see here is that the performance impact in this initial synthetic workload experiment is between 4.9 and 0.7%, and that the longer the transactions, the lower is the impact, basically, on the performance. Same happens when we consider a gem accelerator. So in this case, we have longer transaction. So having longer transaction, we measure a lower impact on performance overall. And this is just the plot of the impact that we have for all of them. So the bottom line is that we have a measured impact that it can be between 4.9 and 0.1%, and it depends considerably on the length of the transaction that are issued by the accelerator. The longer the transaction, the lower the impact on performance that we measure. Now, area and power. We made implementation on different point of target clock frequency for the FPGA. And what basically we can find is that the impact on LUTs and flip-flops is in the range of 5–10%. The power itself measured by Vivado doesn't change considerably. So the measure that we got were considerably very similar. With respect to the overall SoC area impact, if we want to measure what is the actual cost of the access control system in the whole, considering an whole ESP system, the percentage increase that we measure is 1.31% for the LUTs and 0.65% for the flip-flops. If we consider to use a data plane for configuration, that is the one already available inside of the system, so the one that in specific is used for interrupts. But if you prefer to be safer and using an extra data plane and developing the extra data plane inside of the network on chip, in this case, the cost is considerably higher because of the deployment of this data plane, and it ranges between 9 and 10%. So the takeaways here for this project, concluding, is that we presented a security verification framework for securely integrating third-party IPs in a network-on-chip-based platform. We integrated in ESP, but we hope that this framework can be helpful also for other network-on-chip designs. We consider this project to be extensible, so basically both the design and the verification is conceived to be as a baseline for further projects, and we are working as for future plans in extending this security socket also with other functionalities, both for security and safety. And basically with that, we aim to provide something that can support democratize the access to more secure network-on-chip platforms. With this, I conclude. Check out the repo if you're interested. This is the link. These are my contacts. So if you are interested in this work, you want to talk with me, please take my link, take the links and connect with me. I'm going to be around for the whole conference. Thank you for your attention, and if you have any questions.
Thank you. Questions? Please.
Hello, sir. Thank you for the presentation. I have questions. The first one is it the platform Bastion is plug and play, or you need to change the IP
No,
design
it's plug and play with respect to the network on chip, so it's transparent basically. So the IP doesn't even know that there is an access control system.
Means do you need the same specific API to integrate with the IPs?
It's the same, yeah. There is the same interface. From the point of view of the network on chip, there is no change. That's why we decided to put it inside the access control system.
And for the memory addressing, is it the same memory
Yes.
addressing? Okay.
Yes.
No need change for that.
No change. Yeah, exactly. Yeah.
Thank you very much.
Of course.
And the code is available.
Sorry?
The code, the system is available on your repo.
Yeah, the system is developed in the repo. There is a demonstration. There is a fully working prototype on ESP, so you can take it and deploy it. And yeah, there is everything over there. The only thing that is not there yet is the security verification part that is going to be there soon.
Okay. Thank you very much.
More questions? Okay, I had one question, which is, can you say a little bit more about the access control itself? So let's say, like, what kind of security does, like, the security sits in these secure sockets, right?
Mm-hmm.
So, what exactly do they actually offer?
The access control itself.
Yes.
So basically, the system is memory mapped. As of today, ESP allows a tile to access the whole memory map of the system. So basically, if you have an IP that is deployed inside of a tile, it can access everything inside of the system.
Okay,
So-
let me reformulate the question. Access control means authentication or something. Like, what cryptographic mechanism is used?
No, we don't
to
have
this?
authentication. Access control for us is integrity and confidentiality. So basically, we have the system itself as a shared memory or shared resources.
Yeah.
And the tile, as of before this project, could access all of the system. It could access all of the IOs, all of the memory from different tiles, privileged or anything. So we don't want that. We want to let a tile access just some reserved area of memory for the specific tile in the shared memory.
Okay.
So we have the logic that stops that and the management of that coming from a trusted entity, basically. So it's not cryptography.
Okay.
Make sense?
Yeah. Thank you. More questions? No. We thank Francesco again.
All right. Thank you.
And then we move forward to the third and last talk of the session. And I hope I see Daniel. Daniel, yes? Coming on the stage, Daniel, right? Good. If you want, you can move the microphone a little bit up. Then you don't have to, like, Georg, before you were going like this. But you okay? Ready? Okay, so third and final talk of the session is about the design and implementation of a physically secure open source FPGA and toolchain. The floor is yours.
Right. So hello everyone, and thanks for the nice introduction, and let's directly dive into a short motivation. So in this work we want to protect against side channel analysis attacks, which we can mainly divide into two categories. The first one being a passive observation of a device during the processing, meaning that an adversary tries to retrieve information about a secret based on the collected power traces. And then the second category is fault injection attacks, where an adversary injects a fault during the operation of a device, and then based on the changes on the output or non-existing changes also tries to retrieve information about the secret. So in this work we cover both of these attack vectors to some extent, but not in a combined way. And when we want to implement countermeasures in a hardware platform, we basically have two choices. The first one being ASICs, which are fixed during the entire life cycle, and FPGAs that allow us to reprogram them using bit streams, so we have a rapid time to market for new implementations. And to support a wide variety of applications, FPGAs are built with certain hardware primitives to support different use cases, while ASICs are tailored to a specific solution, which only use the primitives that we actually use. So in the use case of side channel security, in the recent years, the trend goes towards provable security, where we deploy some formally proven scheme. And in FPGAs, we can also do this as well, but this comes with a lot of constraints, and so many works rely on some hiding approaches, which, for example, uses balances in routing. So the idea of this work is quite straightforward from this observation, where we want to derive a reconfigurable platform, like an FPGA, and the corresponding tool chain that then generates the corresponding bit stream. However, we want to make this based on a provable secure scheme instead of lookup tables, for example. So when we deploy some formally secure scheme, we rely on masking. And in this talk, this is Boolean masking, which works in the way that we use that we split a variable into d+1 shares to remove the dependency between the power consumption of the data that is processed and the things that the adversary can observe. So we do this by selecting D shares randomly, and they are uniformly distributed, and the last share is then computed based on these D shares and the value to be protected. And then a circuit is considered to be D-order secure if an adversary needs D+1 shares to obtain any information about the secret. And when implementing this, then nonlinear functions play a critical role, as they need to recombine the shares in some way in order to achieve functional correctness. So several approaches exist to solve this, and many of these are gadget-based. So what this means is that we have an unprotected design, and then we can replace each gate or small subcircuit by a provable secure gadget, which is proven by a probing model, and also arbitrary compositions of these gadgets are proven to be secure using so-called composability notions. The scheme of choice that we want to use for our fabric is LMDPL, which is a provable secure first order scheme, and it is mainly divided into two layers. The upper layer is the mask table generation layer, and the lower one the operation layer. So we can execute both of these layers in consecutive clock cycles, and in the case of nonlinear functions, we need to deploy a register stage between these layers. So LMDPL achieves STA resistance using DRP logic style in the operation layer. And this was actually originally introduced as a power equalization technique, but is used differently for the case of LMDPL. And we also want to extend this approach to also get some kind of fault protection. So how this works is that any variable in the circuit is replaced by two rails, where one of the rails is the original value and the other rail is the complementary value. And then we apply alternating precharge and evaluation phases to the circuit, meaning that we can see this in the example at the bottom. First, both rails are reset, and this holds true for all rails in the entire circuit composition. And then in the consecutive clock cycle, we apply the actual values such that we can do our computation. So what we can observe here is that in this protocol, two states are actually unused during evaluation. So one of these is the 1-1 state, which is considered invalid, and the other one is the 0-0 state, which is usually only used during the precharge phase. So we want to use both of these states to indicate a faulty evaluation. Okay, so now let's move towards the fabric. So our concept considers two security regions. The full secure region somehow uses the LMDPL gadgets that I just explained. And then when we implement some cipher, we usually also have some kind of control logic that does not operate on sensitive information or sensitive data. So we can optimize our approach and also introduce a control secure region to realize exactly this. And for this purpose, we can use, for example, the WDDL scheme, which also operates on DRP logic, and therefore can also operate on these faulty states, and we can do our fault detection on these states. But it is not masked, so it's not provable secure. And what this gives us is some composition of gadgets of these two types, where we can put a unidirectional connection from the WDDL to the LMDPL region, and then we can apply synchronous DRP phases to this composition to make them run compatible. And now the approach is to apply the technique of totally self-checking circuits. So what this means is that as soon as in this entire composition, this faulty state 1-1 or faulty state 0-0 is reached, we are not allowed to go back to a valid dual rail state in the succeeding circuit. meaning that as soon as one of these states is reached, it is going to be propagated through the composition until the primary outputs, where it is then sufficient to deploy some kind of fault detector which can detect one of these states. Okay, so before we go to the exact implementation, let's look at how the fabric is structured. So on the left side, we can see this grid-like structure which organizes our CGBs, where each of these CGBs contains one of the gadget implementations, and each of the CGBs is connected to a parallel switch matrix. So we decided to introduce this because in DRP logic, which is then masked, we have 4 wires per variable. So we can actually use 4 parallel switch matrices which share the same configuration. Okay, so I already mentioned that we want to propagate faulty states in some way. And for the control CQ region, we introduced the self-checking WDDL gadgets, which are based on the original WDDL. However, so on the left side, we have the self-checking end version, which needed to be adapted such that also a faulty state 0, 0 or 1, 1 on any of these inputs is going to propagate to the output of the gadget. And additionally, if a fault is injected internally in such a gadget, then it's going to be contributed to the rail that the circuit contributes. In the middle, we have the self-checking WDDL XOR, which is equivalent to the original XOR variant. And on the right side, we also introduced the combined version, which basically computes both outputs. Now that we have these gadgets, we can compose a circuit out of these, and we know that faulty state will be propagated through the entire composition, and we can, as I already said, deploy a fault detector at the output. Similarly, we adapted the LMDPL scheme to the self-checking LMDPL, where we used self-checking WDDL gadgets in the mask table generation layer to also ensure the fault propagation in that layer, such that the DRP protocol is now also executed with 1 clock cycle offset in the layer to the operation layer. And then in the operation layer, also we needed to cover 2 additional cases, namely the cases where any of these inputs is set to this faulty state 1, 1. And then if we would look at this in an exhaustive logic simulation, then we would see that any faulty state is going to be propagated to the output. And most importantly, we did not violate the original security assumption by this approach, because as I said, we are not targeting combined attacks. So if we assume that a circuit is fault-free, then the output of each of these gadgets is going to be tied to 0, meaning that we don't have any additional signal propagation that could leak any additional information. Now that we have these self-checking gadget types, we constructed configurable logic blocks, or configurable gadget blocks. And we did this by introducing some multiplexers on the primary inputs and outputs of the gadgets. And by this, we can invert the rails. So basically, we apply De Morgan's law to achieve additional functionality, like realizing an NAND, a NOR, or an OR gate. We also added an optional register stage, which, because we follow the DRP protocol, has 2 consecutive registers per rail. And then we can implement round-based functions with this approach. What is not visible here is that for the self-checking WDDL version, which is combined, we also added a configuration bit to select between the AND and the XOR output. All right, now let's assemble this together into a fabric layout. So here we can see how the tiles are organized. On the left side, we have some I/O tiles for the full CQ region that are connected to the CGBs inside the linear and nonlinear tiles for the LMDPL part. On the right side, we have some I/O tiles for the control CQ region that are connected to the self-checking WDDL gadget blocks and the unidirectional connection in between. And then we also name the most important global modules of the fabric. So one of this is the DRP phase controller, which generates the control signals that are connected to each of the tiles and applies the synchronous DRP phases. The middle one is the PRNG, which is an unrolled trivium stream cipher. And this one scales with the number of nonlinear tiles in the entire fabric layout. And then the last one is a fault detector, which is connected to all of the I/O tiles as a composition of these configurable gadget blocks is going to propagate the faulty state to the I/O tiles at some point. And then if a fault is detected, then the output is going to be blocked. So now let's quickly look at the tool chain. So on the left side, left top, we can see that we use the Fabulous framework for our approach, which is a framework that allows us to develop custom FPGAs in a grid-like structure. So this is exactly what we wanted. And we adjusted this for our use case and provided a fabric description, which mainly consists of the layout and the interconnections between the tiles, and also a primitive library, which consists of the CGBs. And by this, we designed concrete fabric that we then use in our case study. So assuming that we have this platform, then we also have an automated end-user flow. So a user does not need any kind of pre-knowledge and can just take an unprotected HDL design, then synthesize it with users and use IGEMA to replace the gates with the secure gadget counterparts. And here in this case, we adjusted the library of IGEMA so that we can use the parameterized self-checking gadgets. And then users can translate this by mapping this straightforwardly to the primitive types that are available on the physical device. And NextBNR, which is an open source placement and routing tool, can then, based on the actual availability on the device, conduct the placement and routing in a bundled routing approach, meaning that it only needs to route a single wire, as the other wires are wired similarly through the parallel switch matrices. So in the end, we can generate a bit stream, which fits our custom FPGA if this is manufactured. However, as this is very costly and time intensive, we followed the next best approach by an emulation. So we used a Kintex 7 FPGA on some measurement board, and we took the result of Fabulous, which is a netlist which describes our custom FPGA, and embedded this in the netlist of our measurement setup. So by this, we can then serially transmit the bit stream to the programmed physical device, and by this emulate our custom approach. So we chose a looped AES S-box design for our evaluation, and a custom FPGA layout with 23x7 tiles with a 2:1 ratio of nonlinear and linear gadgets. And we also added a column of control secure tiles. So on the right side, we can see at the top the raw power trace, where the circuit is in idle state in the beginning, and then the looped S-box is executed. And at the bottom, we can see the fixed versus random t-test result after 100 million traces, which does not indicate any signs of leakage. So I want to highlight one comparison that we did in the paper. So here basically we synthesized a selection of ciphers for two approaches. One is our secure fabric, and the other one is the original Fabulous fabric, which relies on lookup tables. So during the synthesis, we only synthesize using the CLBs or lookup tables. And then we compare the gate equivalence that is required for each of these designs. And you can see that our approach is much more efficient, and it is even more efficient if we also include the PRNG. And the reason for this is that the PRNG is embedded in our secure fabric as an ASIC module, so we can save a lot of area overhead with this approach. And we also did some general purpose benchmarks, so we can map arbitrary designs to our fabric, which might not need SDA resistance, so this works, but of course this requires a lot of more area. Okay, so let me conclude the talk. We introduced some methodology to design a fabric which is resistant against SCA and FI attacks. And we also made a case study with a scalable design which relies on the CGBs and the parallel switch matrices. And we introduced the self-checking LMDPL and WDDL variants for the fault propagation. And then we came up with a fully automated HDL design flow for the bitstream generation that fits this fabric with an entirely open source toolchain. And lastly, we also conducted some practical experiments on the emulated design. More details are given in the paper, and our implementations are also publicly available on GitHub. this, thanks for your attention.
Thank you. Time for questions. People are digesting input. I'll start with one, because I went a bit too fast. Can you explain again why your secure version is more compact than an insecure version? That kind of, it's not intuitive, right? You'd like the implementation results? Like you had much smaller area numbers for the secure version, which is counterintuitive?
Yeah, so we took this selection of ciphers and then we protected them using the same design flow. So basically we again synthesized them and used AGEMA to use LMDPL gadgets. And then for a reference design, which is a regular, it's comparable to a conventional FPGA that uses lookup tables, we need to map the LMDPL scheme into the lookup tables basically, which requires a lot of area, while in our approach we can just directly take the configurable gadget blocks.
Okay. So the top part is still protected, but it's like LMDPL in a normal FPGA?
Yes, exactly.
And the bottom side is LMDPL in your way of building the FPGA?
Yes, correct.
Okay. So the top part is also protected, it's just, let's say, in a more straightforward way. Okay. If nobody has a question, I actually have a second question. You said the fault detector sits in the I/O blocks, right? Meaning that if a fault does not propagate until the I/O block, it would not be detected?
Yes, exactly. That's why we ensure in every gadget type that it's actually going to be protected, or some faults that are injected inside a gadget might also be ineffective. So there is no case, there should be no case where a valid dual rail state is set by an adversary by the fault injection. So if an adversary, for example, is able to toggle a dual rail state that is 1-0 to 0-1, then this would be a successful attack. But this is, we consider this as quite hard because the signals are placed very closely to each other, so this should be a very hard problem in practice.
Okay. You had enough time to think about questions if you have any? No? People are eager for lunch. You're lucky. So let's thank the speaker again and all the speakers of the session.
Thanks.